In this lesson, I'm going to show you how we can use rate law information to investigate how the concentration of a reactant changes over time based on the order of the reaction for that reactant. So we've looked at differential rate laws, where the format we've been looking at where the rate, which is in change in concentration over change in time, is equal to some rate constant times the concentration of a reactant raised to some sort of power, which is equal to the order. That was when we were looking at our initial rate data and figuring it out algebraically. Now we're going to look at how concentrations of reactants change over time. So the differential rate laws looked at how concentrations affect the rate of a reaction. This is going to look at how time affects the concentration of a reactant. So as the reaction progresses, their concentrations are going to decrease, but they decrease differently depending on the order of the reaction. This is the AP curriculum alignment. Basically, you're going to be analyzing graphs for this. Sometimes you'll get data tables as well, which is also very simple, but the graphs make it really easy to analyze. You can look at a graph of a reaction, and based on the axis labels, you can determine the order of the reaction off of that. It's just something very quick to memorize. We're just going to look at 0 first order, second order reactions. These two bullet points will be explained through examples. The slopes of the lines you're going to see could be used to get the rate constant. These equations are on the reference sheets under the kinetics section. You only have 4 things under the kinetics section. It's these 3 things and then an equation for half-life. So make sure you always have that little kinetics section handy. I'm going to go through what each of these equations means, what this would look like on a graph. So what we're looking at here were called integrated rate laws. So the rate laws that we looked at initially were called differential rate laws. These are called integrated rate laws. So we would use an integrated rate law when you want to see how long it takes to get to a certain concentration of reactant. See, it says how long it takes till I have like a 4 molar concentration left or something like that. So this is going to relate concentration and time. And you can actually see that in the equation. You can integrate a differential rate law through calculus, but I told you in class that ain't happening with me. You can go hang out with Mr. Fanning if you would like to do that. So I don't do that business anymore. So the rate law for a 0 order reaction that we've been looking at is, rate is equal to rate constant times the concentration of a reactant raised to the 0 power, which is 1. So for a 0 order reaction, the rate is equal to K. If we integrate that through calculus, you get this equation, just in a slightly different form. For a first order reaction, we said the rate of the reaction was equal to K times the concentration of a reactant raised to the first power. This is the integrated rate law. The second order reaction takes this form. This is your integrated rate law. And actually, this bullet here, they revised the reference sheet. It actually gives you the integrated rate law for the 0 order reaction as well. So all 3 of these are on the reference sheet, and they're listed in order. So if you just remember 0 first, second, then you're good to go. Now, what does all this mean? Well, you could just plug numbers in and go from there. Okay, so what all these, in this integrated rate law, what all these letters mean. If I just have A in brackets, that's the concentration, and that there should actually be a sub T there. Sub T. That's the concentration of A at some time during the course of the reaction. K is our rate constant, T is our time. Make sure you're careful with the units, if it's in seconds or if it's in minutes. And then the A sub 0, that is the initial. So that's at time 0, what would the initial concentration of reactant A be? First order reaction, your integrated rate law, same format here, but you're doing natural logs. All the other variables, that should be a T there, mean the same thing. And second order too. So I have over here on a prior 2 slides as well. This is what they look like on your reference sheet. either it's just rearranging it so one thing is on one side or the other side. This should also be AT. Now, if you are looking at a data table and you're trying to determine if a reaction is zero, first, or second order, you can take that data. If you have a data table that has concentrations and it has time, so 0 to, like, let's say 500 seconds, and your initial concentration, let's say it was 4 molar, and it goes down to like 0.06 molar, I don't know, I'm making up numbers here. I could take these points and plot them on a graph 3 different ways. I could plot the straight concentration versus time. I could take the natural logs of those concentrations and plot that versus time. Oh, opposite ways. Sorry. Natural log of a concentration. This would just be the concentration time. And I could also take the reciprocal of those concentrations and plot that versus time. If I did that for my data table, only one of those graphs that I make would be linear. The others will be curves in some way, and I'll show you examples of that. The one that's linear is the type of reaction that it is. And the reason why this works is those integrated rate laws that are listed on your reference sheet take the form of the slope-intercept equation. Not the way that they're written on your sheet, but you can rearrange them to get slope-intercept form. And I'm going to show you that. On your reference sheet, the integrated rate law for a zero-order reaction looks like this. If I rearrange it and I move this initial concentration to the other side, since it's subtraction, if I just add it to the opposite side, I get this calculation, and it's in y equals mx plus b format. So the initial concentration of A is my y-intercept on my graph. The slope of my graph, the opposite of my slope of my graph, is going to be the rate constant. The reason it's going to be the opposite of the slope is because if you plot this, the concentration of my reactant is going to decrease over time. So my slope will be negative, but my rate constant has to be a positive value. A first order reaction, the way that it's written on your reference sheet, is this. If I move this natural log of the initial concentration over by adding it to the opposite side, once again, I get slope-intercept form, where the natural log of the initial concentration is my y-intercept, and again, the opposite of my slope would be my rate constant value. That one would also take on a negative slope if I plotted the data. A second order reaction, once again, if I took this and I added it to the opposite side, I would get my y equals mx plus b format. Now this graph would be a positive slope, so the slope would just be equal to the rate constant. Here's an example. If I took data, concentration versus time data, and I plotted it just as concentration versus time, natural log of concentration versus time, reciprocal of concentration versus time, and my reaction happens to be a zero-order reaction, I would get a linear graph only for that first one, concentration versus time. So if I didn't know it was zero order, but I plotted my data 3 different ways and I got a linear relationship here, I would know that it's a zero-order reaction. You will not have to manipulate data tables and graph 3 different things. You would be given a set of 3 and be asked to pick the order of the reaction based on the graphs. This is if I had a first order reaction. So if I had a reaction that was rate equals K times concentration to the first power, and I used my integrated rate law, and I had concentration and time data, and I plotted concentration versus time. Then I did the natural log of the concentration versus time. Then I did the reciprocal of the concentration versus time. And if this one turned out to be my linear relationship, that would tell me that it's a first order reaction. As a last example, if I had a second order reaction and I plotted data that I had for concentrations versus time, if I plotted concentration versus time, natural log of concentration versus time, reciprocal of concentration versus time, and this graph gave me a linear relationship, that's what would tell me it's a second order reaction. So here's an example. Here's a decomposition reaction. Verify that the rate law is first order with respect to the concentration of N2O5 and calculate K. So I'm given a data table, concentration versus time. So first of all, I would not be able to use method of initial rates to verify this is first order because I'm not given rate data. I'm given concentration and time data, not concentration and rate data. So I would be using the integrated rate law here. So what I could do is I could take, if they're telling me that it's first order, they're telling me to verify it. If I had to do this like in a free response question and it says explain how you can verify that this reaction is first order, you could say plot the natural logs of these concentrations versus time, and if it's a linear decreasing slope, then you would verify that it's a first order reaction. So basically the data table from the prior slide, the natural log of those concentrations was taken, and then those points were plotted. Here's my x value. Here's my x values. Here's my y values. Now the question says to solve for k. So the way that you could solve for k is you can just plug in information from the graph or from the data table into this equation. The other way you could do it is you could calculate the slope, because the slope is the rate constant. So first thing I'm going to show you is just how to plug into this equation. If I have to solve for k, I just pick any value for the natural log of the concentration past the starting point. So I'll go here. The time lapse that took place is 50 seconds. The natural log of the initial concentration, how do I know it's initial? Because that's time 0. And I just plug in and solve. So negative 2.649 equals negative k times 50 plus negative 2.303. That's the natural log of the initial concentration. So when I move this part over, this is negative 0.346 equals negative 50k. Divide by negative 50. And you get k is equal to 0.00692. The other way that I could do this is just by calculating the slope, change in y over change in x. So if I use those first 2 points, so I could do negative 2.649 minus negative 2.303 divided by the change in x, which is 50 minus 0. That would give me negative 0.00692, but since it's a negative slope, I would just take the absolute value of that, so 0.00692. So either way, I can still get the k value. If it asks me for the units, it's telling me it's a first order reaction. So my units would be seconds to the negative first power. Here's just another example. Find the rate law, the rate constant, and the concentration at time 500 seconds. They don't give me the concentration at time equals 500 seconds, but if I know the rate law, I can figure it out. So first of all, I can determine the order of the reaction based on this graph. So the slope is negative, so that means it has to be 0 or first order. And the y-axis is labeled natural log of concentration. So based on the identity of that y-axis and the linear relationship that I have here, that tells me that this is a first order reaction. If it asks me for the rate law, I would say rate equals k times the concentration of A to the first power. Now, it's asking me for the rate constant, k. I cannot solve for k using this version of the rate law. I have to use the integrated rate law based on because I have a certain set of data here. So for the rate constant, I would use my first order to find my rate constant. So I would plug in and solve there to get my values. Since I'm only given the actual concentrations here, not the natural logs. I don't have my calculator in front of me right now, but I think the next slide shows it. You can just plug in any value, natural log of any of these concentrations here. Natural log of the initial concentration would go in that spot. The time lapse involved for the 2 points that you used would be for your time, and you would solve for k. Oh, that's the first part. Find the rate law. We know it's first order. Use that at t0 and some other time. And then the last part of the question, it said find the concentration of A once 500 seconds went by. You would go with your initial and your final, and your time lapse would be 500 seconds. So you would plug in natural log of your initial concentration. This would be your t value would be 500. Your k value we solved in the previous step, and you would be able to get the natural log of the concentration of A, take e to that power, and you will get the actual concentration. I'm actually going to stop there. We're not going to worry about that at this point. We're going to do examples of these in class, how to use graphs to identify them, how to solve math problems with it. I just wanted you to understand that there are graphs involved and that you can represent rate laws of 0, first, and second order reactions in another way.